Hello everyone, Dr. Ross here with a video looking at the topic of matter and the scientific method. So without further ado, I will begin sharing a short presentation. So this has taken all the slides I've posted for the class and I've whittled it down to what I think is the most salient features. Okay, so matter and the scientific method. Okay, so definitely some definitions are in order. So what is chemistry? Well, let me see if I can slightly resize this slide, because I think if I don't, I think my head's going to be over the corner of part of it. Okay, so what is chemistry? Chemistry is, by definition, is the study of matter and its changes. So here I've written study of composition, structures, and the properties of matter and its changes. So the study of the material world, essentially. Matter, if that's what we study in chemistry, is anything that has mass and occupies space. So if you consider some illustrations here, the one with the hydrogen versus electric vehicles, they both consume fuel. So the hydrogen car on the left consumes hydrogen. So hydrogen is matter. It changes because it's consumed. So if you study hydrogen fuel cell cars, you're really a chemist by the definition of chemistry. The electric car on the right consumes charge. Charge is the potential of the flow of electrons. So something is changing. That's why when the car runs out of charge, it stops. It's a real thing when a car runs out of charge. So there's obviously some permanent change happened. That's chemistry. Top right, you have a physician taking care of a patient. From the point of view of the physician, the patient is an object that's made of matter because the patient has mass and occupies space. So in the definition of chemistry given here, a medical physician is a chemist. Bottom right, you've got the stereotypical example of what chemistry is, although I don't recall ever seeing something like that in a real chem lab. I think that's more of a TV thing. But looking at the deliberate changes of chemicals in a wet chemistry lab, obviously that's doing chemistry. And bottom right, we have fuel. Hopefully not too long after this video hits the archives, we'll realize as a people that we need to get away from fossil fuels. I don't know how close we are to that level of maturity, but fuel studying and energy, excuse me, studying energy for the future, that's all chemistry. Okay, so chemistry is such a broad definition, you could argue it's kind of useless because it just covers everything. Okay, so matter, a property of matter is it has mass. So let's have a look at mass. The mass of an object measures how much matter is in the object. We know that mass is proportional to weight. Most people on planet Earth use them interchangeably. But essentially, your mass will never change. But if, for example, if you took an object to the moon, where the gravitational potential is different, its weight would change. So an astronaut, the mass of an astronaut doesn't change on the moon, but they bounce around slowly because their weight changes. On Earth, because the gravitational potential is fixed, the weight and the mass don't really alter that much. Energy is the capacity to do work and transfer heat, which is a pretty lousy definition, to be honest. It doesn't say really what energy is, it says what you can do with it. I don't want to say more than that for now. I'd be aware of this textbook definition, but we'll come back to this lousy definition of energy in a later video when we look at thermochemistry, but not today. We do know, and we'll see in a later video, that energy can neither be created nor destroyed, but you can convert one form of energy to another. So for example, chemical energy and heat energy and nuclear energy. So for example, if you are boiling some water on a gas stove, for example, you're combusting the natural gas to generate heat. So you're converting the chemical energy trapped in the natural gas molecules. You're liberating that as a form of heat energy, which is now going into the pan and the water thereafter to liberate the interactions between adjacent water molecules. So that energy goes somewhere. It just can't be created or destroyed. It has to be accounted for. Okay, so just some definitions to get us going. States of matter. There are numerous states of matter. There's three big ones that become relevant to us. And on the next slide, we look at those plus an extra one just for giggles. But the three big ones are solids, liquids, and gases. You can see this visual on the left here. I believe it's supposed to be a volcano. At least I think that's what it is. And it's to encompass, it's to point to the fact that here in this visual, you have three states of matter, all in the same proximity. So you have, at least for water, I think that's what it is, yeah. So if you look here, the solid, you've got these water molecules. Just for the sake of the diagram, for those that are not familiar with diagrams like this, the red spheres represent oxygen atoms. So what you've got is a red sphere colored in, which is supposed to be an oxygen atom. And then you've got two white spheres next to it like that. And this is supposed to be a water molecule. Not going to say too much more about it. We'll come to this type of visual later in the course. And you can see you have lots of them in very close proximity. It's very hard with the resolution of this picture to see much more than you can see. But if you look very carefully, every time you see a white sphere, it looks to be next to the red sphere of an adjacent molecule. So again, it's in the visual, but it's more than you need to notice right now. But every time you see a white sphere of one water molecule, it's next to a red sphere of another one. That's something that I guess is in the... Also notice there seems to be less molecules in this field of view. And that's because the density of solid water is less than the density of liquid water. It's not really essential that you lift that from this picture, but just in passing, we notice there's fewer masses, there's less mass per unit volume in the solid phase because solid water has a lower density, and that's why icebergs float, for example. Anyway, if we look at the liquid phase, everything looks close together, a little bit closer than in the solid, which is unique for water. Typically, materials have a greater density in the solid phase, but water is pretty unique in that regard. And then look at the contrast with the gas. So large separations. This streaky effect here is supposed to represent motion. So the gas molecules are moving at high velocities. Okay, what's the difference between a vapor and a gas? A gas is a material that's a true gas is in the gaseous phase at standard conditions. So at 25 degrees Celsius and 1 atmospheric pressure. A vapor is not a gas under those conditions, but can be made into a gas. So for example, at 25 degrees and 1 atmospheric pressure, which is approximately room temperature, water is in the liquid phase. So you wouldn't really call it a gas. It can be in the gaseous state. So here I'm kind of using phase and state interchangeably, and I apologize for that. Water can be in the, you can, again, sorry, if you had some water at room temperature, it would be in the liquid state. It would definitely be more like the central figure here, the central picture. So you would say that water when it boiled would be a vapor, because when put back in room temperature, it would be a liquid again. So unless you're a true gas at room temperature, there or thereabouts, then you're a vapor when you hit the gaseous state. So that's very confusing. I can hear myself. It makes sense to me, but I appreciate that you might need to think about it a little bit. Okay. Okay, so this next slide has the 3 important states, for at least for us in this chemistry class, plus an extra one just for giggles. So you could be called upon to look at visuals and then argue what state these visuals represent, etc. So I'm not going to read everything to you. You can read, but just let's look at the diagram. So solids are very uniform and organized. Liquids are much less uniform and much less organized. Gases are the least uniform and least organized. They're the 3 big ones we'll see. This diagram also has plasma. We won't look at plasma in this chemistry class, but plasma is at such extreme conditions that the atomic structure is broken down and you have all the ingredients of atoms, but no one owns those ingredients specifically. So if atoms or molecules, which are a collection of atoms, are just protons, neutrons, and electrons, there's so much energy in a plasma that you've just got a sea of electrons, a sea of protons, a sea of neutrons. So for example, in the surface layers of the sun, that's where you'd see a plasma. Okay. Notice that in this diagram going from left to right, you add more energy. So this is why if you, for example, took solid water, you added energy to that, you could melt the water to make liquid water. You keep adding energy, you could make that into the gas state or a vapor. You add more energy, all the water atoms and molecules break down. Okay, so this slide just looks at changes of state. There's some vocabulary here, so it's essentially a vocabulary slide. So if you look at the way it's arranged in this triangle form here, let's go from the solid to the liquid. So there's some vernacular language here. So if you melt a solid, you can form a liquid, so melting is that process. The reverse process is freezing. So melting and freezing represent a point, or they occur at a certain point. So essentially the melting point temperature and the freezing point temperature would be the same. So for example, temperature notwithstanding, the melting and freezing points are at the same temperature, just going in different directions. Let's go to liquid to gas. We've got condensation and evaporation, and then going from solid to gas, we have sublimation. So directly from a solid to a gas without going via the liquid state would just be sublimation. And if we get the gas and we deposit it to form a solid, then that would be deposition. And then at the top, I've also added some more scientific vocab that we'll need later. So evaporation is also known as positive vaporization. So we essentially form a vapor in the positive direction. The reverse process or condensation would be negative vaporization. So here the positive and negative just represent directions. Likewise, if we look at the solid to liquid state change again, melting later in the course we'll call positive fusion. And then freezing, which is positive fusion in the other direction, therefore becomes negative fusion. So be aware of the vernacular language, be aware of the more academic language. We saw in the previous slide that these state changes occur, or they can be induced by a temperature change. So there's 3 major temperature scales that we need to be aware of in chemistry. The Kelvin scale, the Fahrenheit scale, and the Celsius scale. So there's these equations, you can learn them, you should learn them, you should be able to convert from one to the other. The reason why I point them out here is to look at significant figures. So you'll often be asked to convert from one unit to another, or you might have to convert a unit because you're given a temperature in the wrong scale. So almost all the time in science, whenever you do a calculation involving temperature, always use the Kelvin temperature. So whenever you have to add a temperature value into a calculation, make sure it's in Kelvin. Whenever you need to add a change in temperature, it doesn't matter if it's Kelvin or Celsius, because although they have absolute different values, the change, once you have that value, its incremental change is proportional. So change in temperature, Kelvin or Celsius, doesn't matter. You need just one temperature value, only ever use Kelvin. For the most part, you won't need Fahrenheit in this course. So why we're looking at Fahrenheit, might ask you to convert from Fahrenheit to something else. So it's something you should be aware of. I do want to point out sig figs. So we know from our sig fig rules that whenever you add or subtract, you propagate the least decimal places. Whenever you multiply or divide, you propagate the least significant figures. So we've already learned those. What if you had to convert between temperature units and you had to do a little calculation? You had to figure out, okay, well, if I had this temperature and this many decimals, how many decimals in the converted value? It's all in the equation. So let's look. I'm going to add something here. So Kelvin is Celsius. So this is data. This comes from a measurement tool, an analog tool. So we have absolute uncertainty. We can't fiddle with that. And then we've added this thing here. Well, this is an exact number. Exact numbers have no units, so they have no significant figures. So that number doesn't do anything to the significance of the temperature that you've now produced. So your sig figs for Kelvin are exactly the same as the sig figs for Celsius. You don't alter them. Likewise, in the final two calculations, we've got Fahrenheit and Celsius. They come from a tool. 9 divided by 5 is just an exact number. And the number 32 is an exact number. So these are exact numbers. Likewise, 32 and 5/9, these are exact numbers. So essentially what we've just seen is you don't alter the significant figures when you convert. So don't adjust sig figs when you convert temp units. Okay, because there's nothing in the equation that would allow you to do it. Okay, so here's a nice visual. This is the classification of matter. So again, why are we doing this? We said at the outset that chemistry is the study of matter and its changes and whatnot. You could be called to categorize matter. And even if you're not, you should be able to do it anyway. So if everything that's called matter has mass and occupies space, we can separate that into pure materials and mixtures of material. Why is it important to do that? Well, if you had a mixture, what you observe might be a mixture of the properties of that composition. If you have a pure substance, then the properties are exclusively represented by that thing, and you know that, you've learned that. Let's look at the pure branch first. A pure substance, there's two categories. It's either an element, so it's one of the 118 elements on the periodic table. So there are 118 in the periodic table. So you can have a look at the periodic table. If you see the object on there, you know it's an element, so you could label it thusly. You could also have a combination of elements to form a brand new unique piece of matter, and that would be a compound. So a compound here is two or more different elements that make a new piece of matter. So for example, water here is a combination of 2 hydrogen atoms and 1 oxygen. It's not a mixture because it makes one brand new chunk of matter. H2O is a unit now with other H2O units. So any piece of that material is H2O. So that's it's one type of matter. It just happens to be a mixture of elements. Okay, so that would be an example. Let's now go to the mixture branch. We have 2 types of mixture, homogeneous mixture and heterogeneous mixture. Homo, the prefix means same. So same in this context means looks same to the unaided human eye. So looks the same. It's essentially featureless. So here the example is some vinegar. You look at vinegar, you pour it into a clear glass. It just looks like water, right? You don't see any chunks, you don't see any lumps anywhere. To the unaided human eye, it looks like one object. Although we know it's a mixture because it contains acetic acid and water. This particular brand might have some sugar in it. I don't know. I can't see the label here. But it's definitely more than one type of chemical. Heterogeneous mixture. Hetero, the prefix means different. So here, looks different. Looks different. It has features or lumps and bumps. And here we can see from this salad dressing, we've got what looks like maybe some pepper seeds, I don't know, some oil. We can clearly see a layer. So we can see that this part clearly looks different than this. That's a feature in itself. And then within this bottom layer, there's features within the feature. I can see with the unaided human eye that there's features there, so that's a heterogeneous mixture. Okay, so it's important that we can classify materials. So this visual here, I've added it just because visuals of this nature, apparently, according to education research, cause students an issue. So given this, you could be asked to label pure or a mixture, and if a mixture, which type. Let's look at the one on the left. Clearly, whatever these spheres are supposed to represent, we're told here helium. That looks identical to that, looks identical. I don't see any one of them that's different. If I'm told that that's helium, clearly they're all helium. That's an element. It's one type of element, so it's a pure substance. Looking at item B, we're told this is carbon dioxide. So the black sphere is carbon. The red spheres are oxygen. So carbon dioxide is CO2. So it's got 2 oxygen and 1 carbon. And I can see that that unique chunk of material is identical to that one, that one, that one. So if this were a bag of 6 objects and I blindfolded myself, put my hand in, I would never bring out a black carbon atom or a red oxygen atom. I would always bring out the trinity of CO2. I'd bring out 2 reds and a black, all connected together 100% of the time, because there's one type of matter there. So this is a pure substance. Here, however, we're told this is a mixture. So I'm going to tell you that these white spheres are hydrogen. So this is H2. I've got 2 of them. These red spheres are oxygen. I've got O2. And the blue spheres are nitrogen. So I've got N2. If I put my hand in this bag, I might bring out an H2 molecule. I might bring out an O2 molecule. I might bring out an N2 molecule. I'm going to bring out, with less than 100% probability, something, because there's a mixture. So it's a homogeneous mixture. Why homogeneous? Because I can see that they're different. Well, remember, in reality, you couldn't see hydrogen, oxygen, and nitrogen because it's in my hand right now. Can anyone see all these gases are in the air around you, and we can't see them. So the air in the room that you sat in is featureless. Hopefully, if it's got features in it, you're going to be dead in a few seconds. So hopefully that's not the case. But the air in a room is featureless. So the model represents a featureless room. So maybe that's why students have a hard time with this type of diagram. Anyway, moving on, that's a homogeneous mixture. Physical and chemical properties. There are properties and then there are processes. So let's look at properties first. A physical property of a substance can be observed without changing the substance into something else. So I guess a way to think about this is you can spell correctly as well. Sorry, I've never been able to write and talk at the same time. You can make benign measurements. Benign here just means doesn't alter. So you can make benign measurements on a physical property. So for example, let's look at these two, melting point and boiling point. Why are they benign? Let's say I take a piece of solid water and it just starts to melt, and I put my thermometer into some of the liquid slurry and it says 0 degrees. So I know that the melting point is 0 degrees, but I haven't converted the water into Coca-Cola, for example. I could say, hey, Johnny, come over here, look at the melting point. And Johnny could take a brand new thermometer, not mine, put the thermometer in and say, by Jove, you're right, it's 0 degrees. That's because I preserved the property even after the measurement. So I didn't measure it and now I've destroyed it in the measurement. I've measured it, and because my measurement was so gentle, it was benign, it preserved the property that being measured so that other people could measure it. Okay, chemical property, on the other hand, is not benign. So these are not benign. We permanently damage the property. We permanently damage the material because the property is a hard property. Not benign measurements. So the example here is flammability. Anything that's flammable can be easily combusted, so you can set fire to it and burn it. So for example, gasoline. The reason why we have to go to the gas station and fill our cars with gasoline periodically is because you can't have that property forever. Once you actually execute the flammability and you combust the fuel, it's converted. It's not fuel anymore, it's exhaust gas and what have you. So unfortunately, you demonstrating that property. Look, it's burning. Look, it's burning. Show me again. Oh, I can't now because I burnt it. I need another fresh sample. So these are not benign measurements. So hopefully I've made that at least as clear as I can. So they're the properties. Let's look at the processes. Now, I would learn these together, but keep the distinctions clear in your mind. So they're not exactly the same thing, but they are obviously related. So a physical process is a transformation of a sample that does not alter the chemical identity. So here we've got an illustration of an ice cube. So an ice cube here undergoing a state change. So you can see that the solid water and liquid water, it's starting to melt. It's at the melting point. So the physical property is the melting point. And As we said, that I know that that process, that dynamic process, is benign. It doesn't alter the water molecules. So for example, the liquid here, I have H2O liquid, the L stands for liquid, and here I have H2O solid, the S stands for solid. But other than solid and liquid, which is the state change, I still have H2O. I haven't changed it. Physical processes are reversible. Anything that you can reverse ad nauseum is a physical process because it's benign and it doesn't alter the chemical constituents. On the other hand, chemical reactions or chemical processes are not reversible. So these are irreversible. Cooking, for example, you can't uncook something, you know, oh, I accidentally burnt the toast. You can scrape the burnt bit off, but you've still burnt it. You know, I've burnt some milk. If you've ever cooked milk on the stove and you burn it, you can scrape the skin off of it, but you can never get that taste away because you've altered the chemicals within the milk. The chemistry is irrelevant to us at this point, but you've likely made some ketones. Ketones is a type of chemical that your olfactory senses and your taste and whatnot, and your brain will detect these chemicals. You can't undo that because it's form a homogeneous mixture, and your brain can sense, there's these chemicals in here that belong to this chemical category, and I can detect them. And you skimming off the skin on the milk because you burnt it won't change that. So here in this example, we have hydrogen. We have 2 lots of hydrogen. In the gaseous state, so we've got H2 here and H2 here, so there's 2 lots. And then we've got oxygen, 1 lot, these 2 red spheres here, and they come together to make water and energy. Whenever objects combine, like my hands, there's a release of energy with the visual, there was sound energy. In the chemical regime, it will be heat energy and light energy and other types of things, probably sound as well, but there'll be a release of energy. So we form water and energy. Now, the reason, not the only reason, certainly not the only reason, but one of the reasons why this is irreversible is that energy is hard to keep. So once that energy is released, it's gone. You know, like Joe, Betty, did you grab the energy when it came out? If the answer is no, then how are you going to reverse it? Because you need that energy to go back again. Now you can, if you've lost the original energy, you can add an equal amount of alternative energy. So for example, you could add a battery, like a 9-volt battery, put it in some water, and you will break down the hydrogen and oxygen gases into the constituents again. But that's a different process. You've lost the original energy because you didn't grab it in time. Okay, so I think that's probably everything I wanted to say with this slide. Because chemical reactions are irreversible, they overall tend to be a higher level of energy than physical processes, but much more about this later. Okay, so this visual is nice. This is exactly what I said just previously. You could undo this process and you could take, let's see, you could take 2H2O liquid and you could convert that into 2H2 gas plus O2 gas. And obviously we've added energy as a reactant in the form of a battery. Okay, so this might be how you would make hydrogen fuel for a hydrogen fuel cell car. And this chemistry obviously is what's going on in a hydrogen fuel cell car, and that energy produced there could be used to drive mechanical motion of wheels and what have you. Okay, so the reverse process, if you were to do this and actually capture, you can just about see, and I think it's cool that this has enough information. Let's say this volume is V. You can clearly see that this volume is now 2V. So we've got twice as much hydrogen as we do oxygen, and that's this 2-to-1 ratio here. There's a 2-to-1 ratio of hydrogen and oxygen, and that's how we would know which was which, because obviously they look the same. But because we know a priori there should be a 2-to-1 ratio, and we see it, we know exactly what there is. And we can test for hydrogen and oxygen. We won't discuss that in this video, but there's tests that we could do. Okay, chemicals are represented in different ways, and as chemists in these early stages, we have to get used to that. For the most part, when you write them, and for the most part, when you read them in a textbook, you'll see it as a structural formula as shown. It's important that a student knows that a structural formula, it's important that I stop pretending I can write and speak at the same time. That's most important, right? So structural formulas have no shape information. So it's important that you don't look at this and think, ooh, that's a 90-degree bond angle between the hydrogen carbon and that hydrogen and carbon. No, it's not. It's just a quick way to stick it on a piece of paper so that people can read it. There's no shape information. Just like the English word square, if you wrote S-Q-U-A-R-E on a piece of paper, the reader doesn't necessarily know the geometrical shape of a square. They would have to convert that syntax into a visual representation. Ultimately, that's what a chemist has to do. Ultimately, you've got to see the structural formula, and in your mind's eye, see the space-filling model at the bottom. Shape. This also has shape, the ball and stick model. The bottom one, the space-filling model, is closest to reality. And the ball and stick is just easier to inspect. So you often will read the top one, or if you see the word ethanol, E-T-H-A-N-O-L, your mind's eye would immediately take you to the shape at the bottom, and that's a skill that you would have to work on as a chemist. Okay, so we saw earlier on that matter can be pure or mixtures. So just to remind you of that. Yeah, down here. So we saw that we can have pure substances and mixtures. Mixtures can be separated. Mixtures essentially, let's annotate this now before I forget. Now that we know physical processes and chemical processes, mixtures are only physically mixed. They're only physically mixed. And we know that physical means reversible. So if they're physically mixed, we can, and that's a reversible phenomenon, we can unmix them, right? We can unmix them. There's no such thing as chemical mixing. So we can unmix them. So let's do that. And there are many ways. There's a couple that I'll mention here. There are many other ways that won't be mentioned. Centrifugation, where you centrifuge. So in this example, the visual shown here, there's a blood sample and it's being centrifuged. You can see that the heaviest objects go to the bottom. So typically lowest, it's actually going to be based on density. So the lowest density is going to be at the top. The highest density is going to be at the bottom. So you get a density profile. Remember, density is mass per unit volume. So here we've got plasma and dissolved proteins and sugars at the top of this blood sample. At the very bottom, you've got the plates, the platelets, or maybe the platelets are in the middle, but at the very bottom, you've got the red blood cells, which have extra material per unit volume. And you can separate layers. You could separate the plasma at the top, maybe the platelets in the middle. I don't know if you'd want the actual red blood cells at the bottom. I'm not sure. But anyway, you could separate layers. Now, crucially, blood typically looks homogeneous, right? So blood looks homogeneous, but it can be, don't think I need a semicolon there. So any English majors out there harshly criticizing my grammar. Maybe a comma? Okay. Blood looks homogeneous, but can be separated into layers. Now you could just leave it on the bench overnight and it would naturally separate. You can speed things up a bit by exaggerating the process and decreasing the timeline. The fact that it can be separated, into layers means that it's actually heterogeneous. Because now it's got features, right? I can see this feature clearly from this feature, from this feature, from this feature. I can see features. The whole thing is heterogeneous. So blood is a heterogeneous mixture. Electrophoresis and filtration. Electrophoresis, heavily used in biochemistry and biology and forensics and whatnot, where you, just like centrifugation, where we use density differences to separate. Electrophoresis, we use mass and charge differences to differentiate. So charge and size. So for example, let's say I've got a blob, a small blob, and a large blob. Well, if I have, so this is mass 1, and let's say this is mass 2. So clearly I've got mass 2 is greater than mass 1, right? It's bigger. Okay, so mass 2 is greater than mass 1 in this example. Let's say I put a negative charge, just one negative charge on both. Now, for those of you that haven't yet, go and watch my Basics of Atoms video. When we look at Millikan's oil drop experiment, this is essentially the same thing as Millikan's oil drop experiment. Same ideas. Anyway, so coming back to this video. If you put one negative charge on both, you can manipulate them in an electrostatic field. So the negative charge would be, it's hard to see here, but that's a negative sign, and this is a positive sign. So negative charge is going to be repelled by the negative plate, like charges repel. It's going to be attracted to the positive. Now, when I apply an electric field, it imparts a force. Now, the force is proportional to the mass. So the constant force can affect a small mass to a greater extent. So the smaller mass would move more and the larger mass would move less. So if all of these guys started on the start line here, I would expect the ones that moved further to be lower mass per unit charge, and the ones that didn't move as much to be higher mass per unit charge. So that's how I've used charge and size. Okay, filtration is just using size. So for example, here it looks like a car air filter. You can filter, you know, as the car brings air into its manifold, you can filter out particles of dust and whatnot, or insects. If you've ever brewed some good coffee, and now I really want some good coffee, now I've started talking about it, then you want to use a coffee filter to filter out the coffee grounds. And you can use that as size exclusion. In a biology lab, you can use filtration to sterilize a liquid. You can pass a biological sample which is heat intolerant, so you can't heat it to sterilize it, but you can just filter it through some kind of micropore system that's small enough to allow the specimen to go through, but large enough to allow the specimen through, but small enough that it won't let any bacteria through or particles of virus through. So you could use filtration to sterilize in a biological setting. Okay. Distillation is another big one. You know, in the liquor industry, you can use this to make hard liquor. It's how they concentrate the alcoholic content. I think this visual shown here is probably an oil refinery where you can take crude oil and you can distill away different types of petroleum products. So you could distill away natural gas, send that off as a product. You could distill away gasoline, used as a different product, distill away diesel oil, kerosene, which is jet fuel. And this is all based on a boiling point. So again, what all of these separation techniques have in common, they differentiate based on physical properties. So you can exaggerate the difference between physical properties to separate these physical mixtures. Okay. So matter can come in flavors. So this is a different aspect of matter. You can have intensive properties and extensive properties. Very important that we know the difference. Intensive properties are independent of sample size. So I've highlighted the in here, intensive, independent of sample size. Now, because it's independent of sample size, doesn't matter how much sample you have. So if you have a property that's an intensive property and we all have a different piece of it, we should all be able to come to the same conclusion about a constant value about it. So that's what's nice about intensive properties. An example would be melting point and boiling point, right? I take 1 cube of ice and I measure its melting point, and you've got 8 cubes of ice. We should get the same outcome. Density is another big one. If I take a piece of copper and I measure its density, I should get a value. If I take the Statue of Liberty, the whole thing, I should get the same value as just a piece of copper, because the Statue of Liberty is made of copper. For the most part, here's what I want you to notice about intensive properties. They are fractions again, I did that thing where I'm writing and talking. The fractions x unit over y unit, where both the numerator and the denominator have a unit. And the reason why they're independent of sample size is because if you were ever to scale, then the scale would apply to both the numerator and the denominator. So the scale would cancel itself. So you always return to a constant value. On the other hand, an extensor property is a fraction, but this time it's either x unit over the number 1, or it's 1 over something with a unit. So crucially, with an extensor property, there's only one unit, either a numerator or a denominator. So that when you scale, it doesn't cancel out. So if I were to double this object, it only applies to where the unit is. So it wouldn't cancel, it wouldn't apply to the number 1. So it wouldn't cancel out. So therefore, extensor properties exactly depend on the sample size. Okay, so that's probably good enough for that slide. So density is the big one, at least early on in chemistry, that we need to look out for. Here we can see an example. Density is mass over volume. Mass in units, let's say, of grams or any other mass. Volume in units of milliliter or any other unit. But essentially, if you were to scale this, we're going to hit both and we return the same density. Okay, sorry, I forgot to silence my phone. Incidentally, centimeter cubed is equal to milliliter, so let's not let that become an issue. Okay, because it's a constant, we can use these values to identify unknowns. So density can be used to identify an unknown. So constant, we can use it to identify unknowns and also look at purity. You know, 24 karat gold, 14 karat gold, what have you, 9 karat gold. They're all mixed with other metals, so they would therefore have different densities, and we can use that to categorize them as more or less pure. So if I measure the density of an unknown red liquid and I get a value of 1.06, I've got evidence to argue that I've got human blood. Doesn't mean I'm right, but I've got evidence to argue that that's what I think I have. Okay, so that becomes very valuable. And it's this property, this intensive property, that makes these intensive properties valuable. So this is an activity, and I'm going to just quickly encourage you to try it. So to do it, I've actually got to click on it. So it's supposed to be an active link. If I saved it correctly, click. Okay, there we go. So yeah, it should be loading, but the only way you're going to see it on the video is if I stop sharing this video, and I've got to clunkily go in and share the illustration. I've learned the hard way that these things don't automatically change the sharing. Okay, so hopefully now we're back and you can see this. So I'd encourage you to fiddle around with this. So if I want to figure out the density of, let's say, lead, I would have to weigh the lead. So I've got a value. I then put the lead in here and see the volume displacement. So originally I've got 200 ml of water. So I've got 400, what is that? 4.2 milliliters of water, so I can figure out the density of the lead. Okay. And I could use that to identify the unknown. I could get the mass of the unknown, the volume of the unknown. and then I could figure out exactly what it is. Doesn't matter how big it is. So you don't say it's lead just because it looks like the same size as the lead. You would look at the absolute density. There's a ruler here. This is, in case you want to use some kind of geometry, which is going to be highly inaccurate. I wouldn't try and measure the absolute size of an awkward shaped object. I mean, how would you measure the volume of this using a ruler? You wouldn't. You would just use volume displacement. So the water would naturally mold to the area. Anyway, so these little illustrations can give you a nice gut feeling for how you can identify unknowns based on density and whatnot. Okay, so I'm going to not do what I just did. I'm going to stop sharing that and I'll go back to my slides. Okay, so hopefully we're back. So nice little activity there. Give you some hands-on appreciation for it. 2 more slides left, then we're done with this video. So the scientific method, I have my students do an activity based on the scientific method, so I won't say too much about it here. But definitely science, what is science? Science is a process, or it's a collection of processes. But what are you doing science for? You're trying to understand natural phenomena. There's many ways you can do science. The scientific method is an historical example of how you can do it, but there are many more. Machine-based learning, model-based inquiry, inquiry wheel, a whole gamut of other examples as well. Ab initio calculations, what have you. But essentially, if we look at this diagram on the left, what a scientist typically does, in no matter the field they're in, they'll start by asking a question. And to answer the question, or to start to probe that question, they might make observations. They might do some literature searching and see, has anyone else asked this question before? They might reflect on what they've read. They might reflect on the question. They might say to a colleague, hey, I'm thinking of doing this, can you help me? Are you aware that anyone else has asked this question before? Maybe if it all looks good, green lights throughout, they might do some experiments. They might want to narrow the focus, etc. So there's definitely almost like a pinball. If you imagine the question as a pinball, it can bounce between all of these exterior items and we get this nice webbed effect. Okay, so definitely science here is an iterative process of performance, then reflection, performance, reflection. The difference between law and theories, it's good that we can nail this down now. A law typically is something that you've observed to be true, in quotes, whatever truth means. You've observed to be reliable, but you have no understanding of why it's happening. So a law typically is not something that you have experimental evidence to argue, just something you've noticed, A theory, on the other hand, is something that comes from interaction with a scientist. So a scientist does science however he or she or they want to, and then you come up with some kind of explanation. And crucially, it's this idea of explanation that's at the heart of a theory. No, as of yet, no explanation. That's the difference. Okay, and then our final slide of the video is the scientific method. I just want to point out that this is one of many ways to do science. And because English is my first language, I'm going to get rid of do, and I'm going to write perform. Okay, not to be snooty, but do just looked funny. Okay, so it's one of many historically, and for reasons that we'll flesh out after you do a certain activity for the class. We'll see just that historically, it's just good to know this one, rather than study all possible methods, at least know one of them is the idea why they're always mentioned. So you have a question in mind, something you want to answer because you've observed something. So you've observed a natural phenomenon. So probably you start here. Then you take an educated guess to explain the phenomenon. It's a guess. You've got no reason to think it's correct, but it's a falsifiable guess. Falsifiable. It has to be able to be, you have to be able to do something. If it's a true hypothesis, you can confirm it or deny it. So then you actually do the experiment to try and confirm or deny the hypothesis. You analyze the data. So you either confirm or deny your hypothesis. And you come up with a theory. And then you're either done or you can try and refine it. But importantly, the scientific method is cyclical. You can cycle and cycle and cycle. You can cycle, other people can read your work and cycle. But notice what it's not. It's not like this. You can go around the outside here, but you can also traverse the interior. There's no real traversing of the interior allowed here. You have to perform a cycle and then go back and perform a cycle and go back. So I would say that's the crucial uniqueness of this method versus in general scientific methods. And that will wrap up this overview of matter and the scientific method.